and we can move on to our next speaker, Thomas Bilitewski. So it's actually great to have not just the established senior speakers in our workshop, but also younger people who we may say without offense, who are doing real work. And one thing about our next speaker is that he may be someone who may be able to better appreciate kind of like how widely this concept of soliton is used in many different areas of condensed matter physics. For after doing like in his current position in JELA, and also as a PhD student, he has worked on ultra cold atom theoretical study of ultra cold atom. But in between, with Roderick Messner at MPI Dresden, he actually worked on frustrated magnets, and I think that part actually is more related to the work he's going to present to us today. He's going to talk about long-lived soliton and what one might have thought as a very, very system that everyone knows about, the classical Heisenberg chain. So let's welcome Thomas. And Thomas, so since we have ran a bit over time, I think you should feel free to speak at least until what's the time there now?
Well, it's 8:40 p.m. here, but
8:43 p.m. Okay, so you should feel free to speak till 9:23.
Okay, great. Yeah, thank you so much
After
for
which
the kind
you should take
introduction.
questions. Yes.
Okay, you can hear me. You can see the slides.
Yes.
Okay, great. Thank you so much. Thank you for the kind introduction. And of course, thank you for putting together this great workshop and inviting me. So as you said here, I'm going to talk about kind of from KPZ scaling to long-lived solitons in the classical Heisenberg chain. And yeah, so I kind of started this work while I was kind of working with Roderick at MPI, and in between kind of Masoud joined. And most of the work is actually kind of done by kind of a PhD student at the MPI right now by Adam. So I kind of have a story in two parts. So I'm going to start with kind of showing that we recently found KPZ scaling in the most simple model of classical magnetism, the Heisenberg chain. And then I'm going to kind of talk about how we can understand this KPZ regime in terms of long-lived solitons, which at least to us was a huge surprise to find in thermal states of the Heisenberg chain. So before I go to the topic that I'm going to talk about today, let me kind of talk about a few things that I kind of found very cool recently about kind of classical many-body spin systems or many-body dynamics. So I personally kind of started kind of working in this area, kind of considering classical analogs of out-of-time ordered correlation functions, which we then use to kind of understand chaos in both classical spin liquids, but also in kind of ordering systems in ferromagnets and endoferromagnets. And that's kind of one kind of field that I kind of found very surprising, but there's also other effects that you wouldn't believe might have been quantum. So by now we know classical systems also host pre-thermal time crystals, which originally had been thought to be more or less a pure quantum phenomenon. More related to this classical OTOX, there's also work on kind of kinetic constraints, which I guess then connects to kind of questions of, many-body scarring or kinetically constrained quantum many-body models, but here kind of in classically chaotic systems. Interestingly, you can also use these classical systems to look at things like measurement-induced phases, which again seems like a very quantum concept, but you can actually give meaning to this word also in a classical setting. And what I'm going to talk about today is essentially hydrodynamics of a classical system in relation to kind of KPZ and solitons. And this is kind of work that is kind of published. And for the first part and the second part will hopefully soon be on archive. So before kind of diving into that, why do we actually care about it? So typically the non-equilibrium problem is hard. It's even harder if you deal with a many-body interacting system. And in many cases, nature is kind to us in the sense that many phenomena turn out to be universal, both in equilibrium or out of equilibrium, which then actually makes it a lot more feasible to understand both kind of long time behavior and universally many different systems, even if their microscopics could be very different. And I kind of took two examples where it has been recently been demonstrated actually in quantum systems, where they looked at, again, a spin system, either with long-range interactions or a typical XXZ quantum chain, and they kind of asked how does a kind of the correlations, the spin density kind of change over time, the long-time regime, or how does a domain wall melt? And it turns out that in both of those cases, even though the microscopics are different and the long-time behavior can actually be universal in some sense, so specifically for the XXZ chain and the domain wall melting, they found KPZ scaling, which I would say is kind of, I guess, the most well-known non-trivial universality class. In the sense, of course, you could get diffusion, which I would call kind of the Gaussian, simple, trivial fixed point. And then if you don't get that, one of the options is kind of KPZ scaling, which was originally developed to kind of describe stochastic surface growth. But it kind of turns out in this idea of universality, that it really describes kind of a wide variety of completely different systems. So it describes kind of stochastic processes like a fully asymmetric exclusion process. It also shows up in the theory of random matrices. It shows up, as I kind of discussed here, in the quantum XXZ chain. However, it also is to classical or systems that have a classical limit, like the Fermi-Pastor-Ulam chain or the actually integrable Ishimori chain, which will kind of play a role later. So this is kind of the broader context in which I would understand kind of part of our work here. And we are kind of trying to understand kind of a microscopic system where this emerges, and then really understand what are the microscopics that could lead to this kind of universal long-time behavior. So to give a bit more background about the kind of simple case, so one theory to connect kind of short-time microscopics to long-time universal behavior would be hydrodynamics. And what we are typically asking there is kind of a question of kind of slow modes or locally conserved charges and their long-time dynamics. And then if you kind of write down the most simple equation, so you have a density, you would say the time derivative of density is related to a current, or relative to the gradient of that current in the most simple way. And then you can ask, what is this current? And the simplest thing you can write down, it just depends on the gradient of your density itself. And then there could be higher terms. If you just keep the first term, you essentially get a diffusion equation. And if you get the diffusion equation, you immediately know that the correlators, so the space-time correlators of the conserved charges, show a Gaussian scaling function. So they kind of decay as 1 over square root of t in one dimension, and they have a Gaussian kind of scaling function. More generic, so this is all kind of illustrated in the kind of lower right corner. If you kind of start with localized density, this will kind of just over time diffuse and kind of broaden diffusively. More generally, this exponent doesn't have to be a half, it could have a different exponent, and the scaling function doesn't have to be a Gaussian, it could be any kind of scaling function depending on the problem you're looking at. So how can you get around this kind of story? So there's two kind of, I guess, very well-known cases. If you have a fully integrable model, you don't really have a single charge, you have an infinite number of conservation laws, and then this whole story doesn't necessarily apply. Another way to get around it is if you can kind of make sure that the first derivative vanishes and only higher order derivatives matter, then you also don't get a diffusion equation, but you get something else. And that is actually the case that occurs if you have kind of fracton models. So this is kind of the most basic story about diffusive hydrodynamics. I would say there's two theories that allow you to derive non-diffusive scaling in a somewhat rigorous way. So there is nonlinear fluctuating hydrodynamics, and that is actually a theory that applies to classical fluids or quantum systems that can be described in a fluid language that have exactly three conserved quantities: a mass, an energy, and a momentum term. And this theory specifically has been used to explain anomalous scaling and kind of KPZ-like scaling behavior in the classical easy plane XXZ chain, where the momentum is actually like a phase difference, which at low temperatures is quasi-conserved, which then gives you this third conserved quantity. And that essentially means you kind of have Euler hydrodynamics, but you have a nonlinear term coming from the momentum, and you have some noise term that you have to add phenomenologically to then essentially get the KPZ equation and KPZ scaling. So this is kind of on some level understood in this regime when you have really a fluid with free conserved quantities. A very different approach is kind of generalized hydrodynamics, and that is really a theory that applies here in a fully integrable system. So really you have a system that has an infinite number of conserved charges that you need to describe in kind of a generalized Gibbs ensemble, and where you have kind of well-defined quasi-particles or solitons that then allow you to describe, say, a thermal state as a dense gas of these solitonic particles that ballistically scatter and only interact via two-particle phase shifts, which then allows you to kind of describe the full system in terms of these simple, fully conserved quasi-particles. And this theory typically doesn't directly lead to KPZ. Specifically for the quantum XXZ chain, it has kind of, people have managed to actually kind of get KPZ scaling for the quantum XXZ chain out of kind of generalized hydrodynamics in these two works. So that's kind of a bit of background on why what kind of scaling behavior we could find at long times in both classical and quantum systems. And with that, I kind of want to kind of come to my contribution, our contribution. So in the first part, I will actually show that this anomalous universality class actually occurs in the believed to be fully non-integrable Heisenberg chain, both in the equilibrium hydrodynamics as well as in equilibration dynamics. In the second part, I will show that not only does it have anomalous scaling, actually there are lots of single and two-soliton solutions of the Heisenberg chain that people didn't know existed, as well as establishing that thermal states can actually really be understood to some degree as being composed of well-conserved solitons that scatter ballistically, which then explains why the Heisenberg chain actually could show KPZ scaling, because we actually have kind of well-defined solitons in this system. So I guess everyone knows the classical Heisenberg chain. So it's really one of the simplest interacting classical many-body systems. So we have kind of spins that classically is just a vector that has three components of norm 1 that we put on the kind of the sides of a one-dimensional lattice, and they interact via nearest neighbor Heisenberg exchange, which can either be ferromagnetic or anti-ferromagnetic. And then this Heisenberg Hamiltonian can induce dynamics in terms of the Landau-Lifshitz equation, which you can very simply understand in just saying that the time evolution of a spin on a side J is just the precession of spin J in the exchange field of its two neighbors, which you can also understand in terms of kind of spin Poisson brackets. And then the quantities we're interested in for this kind of simple system is the connected correlators for spin and energy. So we're going to ask, what is the long time and long distance behavior of the spin-spin correlation function, as well as the energy correlation function, where the energy on a bond is just the dot product of the two spins across that bond. Where again, for the energy, we kind of need to subtract the expectation value. Whereas for the spin correlation function, we don't have to do that because in bond dimension at all temperatures, there's no magnetization. So the system is always unpolarized on average. So with that, let me tell you, but it's actually an interesting question. So you could imagine that this Heisenberg model, this most simple model of magnetism in 1D, we would know what the hydrodynamics is, but we actually don't. So there's kind of work from the 90s up till 2020 that claims it should be diffusive at least at infinite temperature, and in many works also at all finite temperatures. In contrast, there's some work going back to the 90s and also up to 2020 that claims it's actually non-diffusive, both at infinite temperature and at finite temperatures. There's some works that say it is diffusive, but the diffusion constant itself has a logarithmic correction, which then was refuted by another paper which said, well, no, it's actually not a logarithmic correction. It's actually perfectly diffusive, but there is a 1/square root t correction. So you're already seeing that there's a lot of debate spanning 30 years of what the hydrodynamics of this model should be. And so we kind of thought maybe we can shed light on some of these questions. So many of this work have some analytical treatment, but many of them also have numerical parts. So we mostly work numerically, and we mainly, I guess what we achieved is we have considered considerably larger systems for considerably longer times, over the full temperature range from essentially 0 up to infinite temperature. And our kind of main findings are that there's a really qualitative difference between a ferromagnet and an antiferromagnet in terms of the hydrodynamics. Specifically, the ferromagnet will show KPZ scaling and have solitons, at least at low temperature. And with that, kind of let me briefly look what we are doing. So it's classical systems. So we can easily simulate up to 10,000 spins. We then can prepare a thermal state by just sampling from the canonical distribution function at a given temperature or energy just via Monte Carlo. And then we're just gonna kind of solve the equations of motion for times up to 10 to 5 times the exchange constant, so 10 to 5J. So we're really, in many ways, in a better situation in quantum systems where you might be lucky if you get up to 10 or 100J, you can easily go up to 10 to 5 exchange constants to really access the long-time hydrodynamic regime of these models. And technical detail, in principle, in all these simulations are, of course, numerical, but they're essentially well conserved enough to kind of conserve all the conservation laws we care about on a physical level. And with that, kind of let me go into some of the results that we kind of find. So I'm going to start with the observables. Again, we look at the energy correlation function and the spin-spin correlation functions. And we're going to ask if these correlation functions show some universal scaling with generically some exponent alpha and an unknown scaling function. This exponent alpha doesn't have to be extracted from the full space-time dependence. You can instead look only at the autocorrelation function, which is the correlation function evaluated at x equals 0 as a function of time. And if you have this kind of universal scaling, then the autocorrelator just scales as a power law of the exponent alpha. And then given this correlator, we can also ask, is there some crossover between, say, inverse T correction, or is there logarithmic correction to the diffusion constant? Really answer some of these questions that have been posed by the predictions in the literature. By really simulating these systems for large enough times to kind of make strong claims here. And the first thing I'm going to look at is the energy correlations here at some intermediate energy or temperature in the left plot for the antiferromagnet, in the right plot for the ferromagnet, and they turn out to be fully diffusive. So I'm plotting the correlation function by rescaling space by square root t and rescaling the magnitude of the correlation function by square root t as well, such that I get a scaling collapse onto a Gaussian, which tells you these correlations are kind of fully diffusive. And this is true at infinite temperature, it's true at finite temperature, it's true down to 0 temperature, with some caveat that that you have some ballistic part of the energy correlations due to spin waves, at least for finite times. But essentially, this is fully diffusive, and this is what you would have naively expected. Now you can look at the spin-spin correlation function at infinite temperature. And again, we find that both for the ferromagnet and the antiferromagnet, which at infinite temperature are exactly the same, so there's no distinction here, classically, turn out to be perfectly diffusive. So again, we can first look at the autocorrelator, which should show an exponent alpha. So if I just multiply that by square root t, as done in this left plot, we see this nicely converges to constant value, which tells you this shows perfectly diffusive scaling. In addition, it also tells you there is no log correction here. If you believe this log correction for the diffusion constant, this would have to go down to 0, which it doesn't do. So this essentially excludes the diffusion, the log correction on pretty long time scales. So as I said, we go up to 10 to 5J. In addition, you can also look at the full correlation function, again, in the right-hand side with the diffusive scaling at high temperature or at infinite temperature. This perfectly collapses onto a Gaussian. So this is perfectly diffusive. Everything is good at infinite temperature. Now what we're going to do next is we're going to go a bit lower in temperature and kind of see what we see. So at high temperature, so not quite infinite temperature, but at high temperature, the ferromagnet in blue and the antiferromagnet in orange both show kind of a power law decay of the autocorrelator that is consistent with a half. So they show both diffusive scaling if you are at high enough temperature. Now, was really surprising to us is if you go to lower temperature, suddenly the ferromagnet behaves completely different to the antiferromagnet in the sense that the exponent of the power law decay of the autocorrelator actually has an exponent that is close to 2/3, whereas the antiferromagnet stays very nicely diffusive at all temperatures. So what we're finding here is that the ferromagnetic spin correlations are anomalous, super diffusive, specifically at low enough temperature with an exponent that is very close to the KPZ values of 2/3. So that we kind of found interesting. So we kind of looked at it a bit further. So you can again look not only at the autocorrelator, but at the full correlation function. And you can ask, do I get a diffusive scaling collapse or not? If you look at the antiferromagnet, that shows perfect Gaussian scaling collapses both at high temperature and at low temperature. So that is always consistent with nice diffusion. The ferromagnet is again only consistent with diffusion at a high temperature, whereas at low temperature, you have to really use a generalized exponent alpha, which again is very close to 2/3 for the temperatures I'm looking at here. So at this point, we kind of know this exponent seems to change with temperature, at least for the ferromagnet. And specifically, you can ask, how does it change? So at very high temperature, which is this lowest curve I'm showing here, this is kind of at infinite temperature. This is a power law decay with exactly exponent a half. If you kind of go down in temperature, this exponent increases, and at exactly t.2, you actually get a perfectly straight line fit over 4 or 5 orders of magnitude to with an exponent of exactly 2/3. So I'm mainly showing this plot here to make one important point. You kind of see that these lines seem to have finite time corrections, and they seem to be below the power law here, and the simple power law seems to be above at very low temperature, where it appears that exactly at t.2 you get the most straight line fit, which is kind of curious. So if you assumed it would be finite time corrections that somehow change this exponent from a half to something else, then for some reason exactly at this temperature it seems to vanish, and you exactly get a perfect power law with exponent 2/3. So all of this was now the correlation function. You can look at this exponent as a function of energy, and as I said, for the antiferromagnet, it's always consistent with half in orange. For the ferromagnet, it seems to increase with temperature and saturate somewhere close to 2/3. So you could believe maybe we didn't just do a good job. We kind of we have numerics for finite times. So maybe this is not the real exponent. So let's believe there's a crossover from this exponent to a half. And you can ask, what would be the crossover time such that we didn't see it? And if you kind of extract such a crossover time and again plot versus energy, you kind of see this seems to blow up for the ferromagnet. So if you believe there's a crossover at super long times, then this crossover has to be beyond 10⁷ exchange constants. So it could very well be that eventually it becomes diffusion. However, if it does, it really happens at astronomically large times. So this is all about this exponent. Now, the most convincing evidence is again looking at.
Hi, Thomas.
Yeah.
Yeah. Can I ask a question?
Yeah.
Okay. So yeah, just to clarify, so this for the finite temperature effect, in your simulation, how did you capture that effect? Did you?
All right. So it's classical system. So I have a 1D Heisenberg chain, and I literally prepare a fully thermal state from the canonical ensemble. So I literally sample E2 minus beta H. I get a spin configuration. I do dynamics, and then I choose 20,000 spin configuration at the temperature and average everything.
But yeah, during the evolution, time evolution.
Right, energy is conserved. Energy is conserved during time evolution. So
energy conserved. Initial conditions are prepared according to this Boltzmann.
Yeah, exactly. So in 1D, for the Heisenberg chain, energy and temperature are the same, right? So you can choose either, and you fix the initial energy density, which corresponds to temperature, and that stays the same during time evolution.
Okay, thank you.
Yeah.
A follow-up question, Thomas. What about the other integrals of motion? What else is conserved except for the energy?
So the known ones are, of course, magnetization and spin length and energy. So those are the ones we know, and I assume that for the Heisenberg chain, there's no other known conserved quantities.
So how do you deal with them when you prepare your distribution? You said you take the Gibbs distribution, but how do you fix?
Boltzmann. I take E2 minus beta H. I don't fix magnetization.
Which means what? Which means that you mix different magnetization values?
Right. So in principle, you fix different magnetization values, but the distribution in the thermodynamic limit of M is narrow around 0 at all temperatures.
Thank you.
So there's a distribution of M. Each sample has some M, but on average, like it is narrow around 0, and the width goes down compared to the fluctuations. So yeah, it's very close to 0. I think numerically it might be 10 to minus 5 or 6 for most typical samples.
So again, the magnetization is conserved, right?
Yeah.
So therefore, you could choose different values and look at the dynamics of at each fixed magnetization.
I could do a microcanonical ensemble that fixes both energy and magnetization. That's correct. Yes. So we average over those in a canonical way. That's right.
Thank you.
Right. So yeah, I want to say this is now really the correlation function. So this is the spin-spin correlation function, and we use the KPZ exponent to rescale time or space and the magnitude, and we compare to the KPZ scaling function and the Gaussian here. And we kind of clearly see that the numerical data is very much inconsistent with the Gaussian and is perfectly consistent with the KPZ scaling function. So this, I would say, constitutes very kind of strong evidence that at least for a time scale up to 10 to 5j, I see perfect collapse onto a KPZ scaling function for the Heisenberg chain. And I also later comment on this is essentially as good evidence of KPZ scaling as anything we've ever found in any model. So if that kind of let me kind of go to the equilibration. So everything I've talked so far was about equilibrium correlation functions. So the second thing we tried is, okay, imagine we do a quench from the XY chain, and then we ask how do observables in the model thermalize to the expectation values that you would have expected for the Heisenberg chain. So it's a quench from the thermal state of the XY chain into the full Heisenberg chain. And we are asking how does the system relax? And again, we can look at different quantities. We can look at kind of measures of essentially the spins. We try to choose the anisotropy and these kind of component resolved bond energy, and kind of a measure of the energy distribution, which is essentially a variance of the energy over the chain. So this is meant to kind of model kind of what the energy would do, and those two are meant to model what the spin degrees of freedom in our model do. And most naively, you would expect that they also decay with some power law towards the equilibrium values. So that's the kind of basic question we are asking, and it's roughly consistent with what we saw in equilibrium. Again, the antiferromagnet is always diffusive. The ferromagnet for the energy like observables is also diffusive. If you consider a spin-like observable, it suddenly has exponents that strongly depart from diffusive scaling at finer temperatures. And again, it could be that they become diffusive at even longer times, but if only approach the equilibrium value to the kind of order of 10 to minus 4, there's a question of whether you care if the super long-range tails might be something else, because most of the equilibration was clearly non-diffusive. And then we can kind of, again, extract these exponents as a function of energy density and just compare to the equilibrium values. And they are not quite the same, but they kind of show the same picture for the antiferromagnet. They kind of go up at low energy, and there's some differences between them, but they're broadly consistent in terms of the qualitative picture between equilibration and equilibrium exponents. So with that, let me conclude this first part. So what we found is that the energy correlations are diffusive for both ferromagnets and antiferromagnets at all temperatures, with kind of finite time ballistic correlations at very low temperature. They kind of emit kind of sound waves or spin waves. And that's true for kind of both models at all temperatures. Kind of in contrast, we found that the spin correlations for the ferromagnet are super diffusive, at least for very long times at low temperature. And we found essentially as perfect as we've ever seen KPZ scaling at this regime. Whereas the antiferromagnet chain is always just purely diffusive. So I want to point out one thing. Of course, I'm saying this is low temperature. So you could say maybe there's some connection to maybe the continuum limit or something else. So at this temperature, the correlation length of your spin chain is, I think, 5 lattice sites. So it is low temperature, but in terms of correlations, it's really not a 0 temperature state at all that we are looking at here. So with that, we kind of found that this Heisenberg chain, this most simple model of a magnet, actually hides this rich regime of super diffusive spin hydrodynamics that people weren't aware of before. We found this very strong evidence of at least long-lived KPZ scaling. And now we have to wonder, where does it come from? And as I mentioned, you could just think, okay, we know the continuum model is fully integrable. So maybe it is just continuum physics that kind of shows up here for at least some time. So what I don't like about that explanation is that we really have a short correlation length here. As I said, like 5 lattice sites, and claiming that the full spin physics is in the short or the long range length limit where I can think of it as a continuum system doesn't quite sit right with me in this regime. Of course, the second explanation is there could be an integrable lattice spin chain around. And that is what I would argue for is maybe the better explanation, which also kind of fits into the second part of my talk, where I will show that we can find solitons in the Heisenberg spin chain that are very closely related actually to an integrable spin chain. That is maybe not close, but at least you can connect it to that integrable model. And that's kind of the second part of my talk, where I will now kind of discuss how we very recently found solitons in the Heisenberg spin chain. So as I said, we kind of know the continuum model is fully integrable. We also know there's a lattice version, so the Ishimori, or alternatively called the integrable Landau-Lifshitz chain around. But generically, people would have said the Heisenberg chain is non-integrable. So we kind of looked in literature. There's some approaches where you kind of do kind of a continuum discrete mixture, where you kind of look at modulated spin waves, which kind of look a bit like solitons, but are not quite the same. And there's some kind of exact solutions that are kind of periodically not moving, they're periodically, I'm not sure if you could call them briefers, but they are periodic exact solutions of the Heisenberg chain, but they are also not solitons. So as far as we know, I guess this modulated spin waves is the closest thing to people having looked at solitons in the Heisenberg chain before. However, kind of there is this integrable Ishimori chain. So for those that don't know that model, it is very similar to the Heisenberg model. So it's again a lattice model of classical spins with length 1 three-dimensional vectors. And instead of s.s, the direction is now the logarithm of 1 plus s.s. So that's the only change. And it turns out that Ishimori in the 60s, 70s actually figured out that this model can be directly mapped to the discrete nonlinear Schrödinger equation, which then means you can it's fully integrable the same way that the nonlinear Schrödinger equation is. You can write down both the one-soliton solutions and the many-body soliton solutions exactly. You know exactly the two-soliton phase shifts for that model, and you can describe the full thermodynamics of this as a soliton gas or via the thermodynamic beta ansatz.
Sorry, Thomas, question. Which discrete nonlinear Schrödinger equation are you referring to, which is integrable?
Right. I would have to look in Ishimori's paper which one it is specifically. So it's the where you put the nonlinearity psi to the 4 into the differential equation, but I'm not sure which coefficients you need specifically for this one. But I think it's both in Ishimori's paper, specifically the mapping, how that works out. So I would have to look up which discrete nonlinear Schrödinger equation it actually maps to, because there's more than one integrable one, if I remember correctly.
I know only one, which is the Ablois-Ladik chain.
Right. If there's only one,
that one has this nonlinearity in the coupled to the discrete Laplacian. While the standard nonlinear Schrödinger equation, where I just have the nonlinearity sitting in the local potential, that's non-integrable. So that's why I'm asking, which one is it here?
Yeah, I would have to look it up what Ishimori specifically mapped it to. The mapping is somewhat non-trivial, I guess. But yeah, I mean, that one, from what I said, is fully integrable. So if it's only one, that must be the one it maps to.
Sure. Thank you. I'll check.
Yeah. And again, since it's fully integrable, there's an infinite number of charges. One charge I want to point out is the torsion, which again, you wouldn't have guessed that this somewhat complex quantity is conserved, but it turns out this quantity is conserved. And I want to point it out because that will be useful also to understand the Heisenberg chain case a bit later. And not only is this model integrable, very recently, Herbert Spohn and co-authors actually showed this shows KPZ scaling. And in the more recent work, they also showed that this KPZ scaling is actually robust to symmetry-preserving perturbations, way beyond what you would naively expect. So you can go into the regime where this model is already chaotic, but KPZ scaling still seems to persist. So that kind of is kind of interesting, and we're kind of wondering, can we kind of make that a bit more quantitative for the Heisenberg chain case? And just to kind of compare this is the evidence for the Ishimori chain for KPZ scaling. This is all evidence in the Heisenberg chain, and up to different y-axes, essentially the evidence is the same within the above the noise floor. So if you believe this chain has KPZ scaling based on this plot, you would also believe that this one has KPZ scaling based on this plot. With, of course, the caveat here, we at least know that it actually are solitons because it's fully integrable. But from the numerical evidence, it's equivalent, I'd say. So with that out of the way, let me maybe tell you briefly what the solitons of the Ishimori chain look like. So this is kind of a soliton that you can get. You can write it down analytically. So I plot the Z components and the XY components as a function of the lattice position in a 1D chain. You can write down explicit expression for those. They're kind of somewhat complex. The only thing that matters here is that they have two parameters, R and K, that fully determine the one soliton solutions. So that's all I want you to take home from these equations. There's two parameters, R and K, that allow me to write down one soliton solutions of the Ishimori chain. And they kind of have physical meaning. So as I said, there's two parameters, R and K, and you can understand R essentially as an inverse width of your soliton. So if you kind of ask how wide is, say, the Z components, or with a prefactor, the XY components of a soliton, this scales as 1 over R. And the K is essentially a momentum. So if you don't only look at a stationary soliton, if you kind of look at a moving soliton versus time, they kind of have one soliton at the initial time, at a later time, and a later time, this moves with a ballistic speed V, and this ballistic speed V can be related to R and K. So K in some sense is something like momentum for this soliton, or speed like quantity, and also determines how fast the XY components rotate, which is kind of given by this internal rotational frequency of your soliton. And just to show you a movie, this is kind of what a soliton does in the Ishimori chain. So as you expect, it's a soliton. It's a nice localized excitation of above a vacuum that kind of just ballistically moves essentially forever. And this is kind of the movie I want you to keep in mind when I will go next to the Heisenberg chain, where I will essentially find exactly the same kind of solutions for the presumably fully non-integrable Heisenberg chain. So it's moving ballistically, there's no dissipation, this can go on essentially forever. I will stop this movie at some point. And this is kind of one of the new results we have. We kind of find one soliton solution in the Heisenberg chain in a wide parameter regime. So maybe let me explain this plot. So I plot kind of an existence diagram for one soliton solutions for the Heisenberg chain as a function of this K, which is like a velocity, and this is function R, which is an inverse width. And we get those by an explicit construction for stationary solitons. So along this K=0 line, we can explicitly construct them exactly. And for finite velocities, we can construct them by adiabatically connecting Ishimori solitons to Heisenberg solitons. And within this yellow region that works, within this kind of bluish region, it doesn't. So we can't prove that there can't be solitons here. We just haven't found any here. But essentially, there's an infinite family of solitons, one soliton solutions parameterized by these two parameters. And as I said, for stationary ones, they exist for all widths. So you can have a soliton that essentially has a width of one lattice side, the Heisenberg chain that lives forever, which I found very surprising and wouldn't have expected. And then, which I guess physically makes sense, as you make them faster, only wider solitons survive in the Heisenberg chain. And then maybe to explain you how we got these plots, well, no, first of all, I want to show you them. So this is now a Heisenberg soliton. In the upper plot in the kind of short time scale and length scale, and the lower plot is really long times and long length scales. So again, the upper one looks exactly the same as the Ishimori soliton. It just ballistically propagates through the Heisenberg chain essentially forever, which you can see in the lower plot. So this is now for longer time. So it's the same soliton, it just looks a bit more narrow because I've kind of zoomed out. And this kind of now continues for 10,000 J. And this soliton will kind of propagate ballistically without dissipation essentially forever, as far as we know. We've never seen them decay, independently of how long we evolved the equations of motion. For the solitons that live in this yellow region. So this is kind of the first, kind of the broad overview of the one soliton solutions. And now I'm going to kind of tell you how we get them. So the stationary ones, we just use an ansatz. We assume the Z components are stationary based on what you know about the Ishimori solitons. And we assume that the phi angle, which gives you the XY components, is essentially uniform across the lattice. And we assume it also just rotates with a uniform speed. And you can just put this ansatz into the Heisenberg equations of motions, which gives you a consistency equation, which relates the derivative of your rotation speed, which is constant by assumption, to the Z components on 3 lattice sides. And you can rearrange this equation essentially in a form where you say I can determine the Z component at side I if I know the rotation speed and the Z component at I+1 and I-1. And that now gives you a numerical construction how to get it. So you fix omega, you fix the center soliton to be -1 because that's what the soliton should be from the Ishimori chain, and you just choose some random value for all other spins. And then you solve for Zi. If you know the one neighboring spins, you sweep through the lattice, and this essentially defines a contraction on the configuration space of spins. And it turns out numerically this converges for all omega. So to show you this is kind of our initial condition. I put the soliton in the very center, exactly at -1, and that shows some random value for all other spins. And I literally just sweep through this lattice solving this equation, and you see that in 10 sweeps, it fully converges to a fixed solution, to a nice soliton that is now an exact solution of the equations for the Heisenberg chain. And maybe if you don't believe this movie, you can also ask, does this solution satisfy this consistency equation? And what I'm plotting here is the error in the consistency equation as a function of the sweep number on a log plot. So you see this actually decreases exponentially as a function of the number of sweeps I do, and it plateaus at a value that increases exponentially with the system size. Of course, a finite size system might not have a perfect soliton, so that's expected, but already for 100 sites, the error I get is below 10 to -20, so it's below machine precision. And it keeps decreasing as you make the lattice larger. So this procedure essentially defines an exact soliton solution of the Heisenberg chain for all omega, or alternatively for all VIPs R. So this defines exact solution for all VIPs for a stationary solution of the Heisenberg chain. And then the second thing is to construct the moving solitons. And what we there do is we kind of adiabatically connect the Heisenberg and the Ishimori models. So we kind of write down an interpolating model where we introduce a parameter gamma that for gamma equal 1 just recovers the Ishimori chain. And for gamma equal 0, the limiting case is the Heisenberg chain. So that's a nice smooth interpolation of our Hamiltonians. And importantly, it's O3 symmetric for all gamma. So I really preserve the symmetry, which is kind of important from the intuition we have that symmetry preserving perturbations might not break integrability too much. And so what we do is we kind of take our Ishimori soliton, which you know exactly, and then we sweep our gamma as a function of time smoothly from the Ishimori case, the Heisenberg case, and we kind of ask what we get. And we get a Heisenberg soliton that by I looks pretty much the same. At least if you start with these solitons, you can kind of ask if this process is really adiabatic in a bit more quantitative way. So what you can ask is, does the soliton ever emit anything? So you can ask, is there always a unique defined minimum of my Z profile? This is plotted here as a function of time in this adiabatic process. And for these solitons, it works. So you never emit anything. There's no pulses emitted. It's all smooth deformations of this soliton into this final object. And that is true independently of which adiabatic time you choose, as long as it's large enough. So it's really a smooth adiabatic process that nicely converts this soliton to this soliton without any dissipation, within machine precision. This isn't always true. So if you take a fast-moving, very narrow soliton, what you're going to see is that instead of having only a single minimum as a function of time, you're going to emit lots of solitons. You're kind of really dissipating lots of pulses, which then leads us to believe there shouldn't be a soliton for these parameters in the Heisenberg case. And not only does it emit all these pulses, you actually emit more pulses as you do it slower. So really, the soliton doesn't want to live in the Heisenberg chain from an intuitive level. And this then essentially defines this existence diagram where, again, the zero line we know exactly, and anything else is given by this adiabatic connection. And in the blue region, it just didn't work. So this tells us what one soliton solutions we have. Again, for the Ishimori chain, these parameters R and K also give you the energy, the velocity, the rotation frequency, and the torsion for these solitons, which are all good conserved quantities for the solitons themselves. We can ask, did it change as we created a Heisenberg soliton? And this kind of what these plots are showing. So I'm showing kind of the rotation frequency, the energy, the velocity, and the torsion as a function of the width for different velocities up to the point where they cease to exist. So these dotted points are the Heisenberg solitons, the solid lines are the analytic results for an Ishimori soliton, and the dotted points stop when there's no soliton anymore for the Heisenberg case. But the main point here is, without understanding the details, is that they are almost the same. So the Heisenberg solitons by I, or in terms of these internal properties, are almost indistinguishable from the Ishimori solitons. So this kind of now establishes these one-soliton solutions. You could ask, do they also scatter? So for the Ishimori case, again, we know it's integrable, which means scattering should be fully ballistic. And the only thing that can happen to two solitons that scatter is that they experience a phase shift, which intuitively you can understand in terms of kind of a time delay. So two solitons move in, they meet each other, they go out, and they have still the same speed, but they could have been delayed a bit via the interaction with a second soliton. And that's analytically known for the Ishimori case. We can ask, is the same true for our Heisenberg solitons that we just constructed? So we do two soliton scatterings for a Heisenberg chain. So there's a function of x and t. I'm plotting here the SZ on a color bar. So there's an incoming soliton here. There's an incoming soliton here. They interact and they move out. And asymptotically, they move at exactly the same speed as the speed they came into the collision. And there actually is a phase shift. It's kind of hard to see in this plot, but I'm going to later actually specifically look at what the phase shift for this collision is. And you could say, okay, maybe I got lucky. They survived one collision, but not many. They actually survived hundreds of collisions. So here, it's the same plot, just zoomed out. There's a fast-moving soliton kind of here that kind of hits a white stationary non-moving soliton here, which is this white yellow region. And you see each time this fast-moving soliton hits the fast narrow soliton, each time it hits the stationary white soliton, this soliton just moves over a few sides, and then it's again stationary. Next collision, it again moves over. It doesn't move. It gets hit again, and it moves over, and then it does nothing again. So it really, and both the moving soliton and the stationary soliton are stable up to hundreds of collisions. So really, this is exactly what you call a phase shift. And this is now a movie of that. So this left peak is the fast-moving soliton. The right peak is the non-moving soliton. And I can show this. This is now a very fast movie. So this fast-moving soliton will move right, hit the soliton, and deterministically shift it over a few lattice sites. So it hits it, again. And each time this peak moves exactly some number of lattice sites for each collision. And if you look at the time scale, this is in units of J. So these solitons survive hundreds of collisions and up to easily 10,000 J without any dissipation. So neither the fast-moving soliton nor the stationary soliton emits anything throughout this process. So they perfectly scatter ballistically, essentially forever as far as we know. And this allows us to define a phase shift. So this is now the comparison of our Heisenberg extracted phase shift from these collisions as dots versus the analytic Ishimori phase shift as a function of R for this collision process where fast-moving soliton hits a stationary soliton. And there is some scatter due to numerics, but again, it's only very mildly renormalized. So for all intents and purposes, they scatter almost ballistically with a nice phase shift as in the Ishimori case. So this now tells us, okay, we have two soliton solutions that live essentially again forever and scatter almost like proper solitons. You could now ask, all of that was only two solitons in a vacuum. Does any of that actually apply to a thermal state? So what I'm plotting here is a thermal state of the Heisenberg chain to the left and the Ishimori chain to the right as a function of space and time. In the upper plot, I'm going to plot the torsion, which recall this is an exactly conserved quantity for the Ishimori chain that is carried ballistically by each soliton. So that's why you see perfectly ballistic lines in the right plots, which are single solitons that move and that carry a certain quantum of torsion in a thermal state, which makes sense because the Ishimori chain is fully integrable, so it is just a dense gas of solitons. Interestingly, there are strong remnants of this even in the Heisenberg chain. So in the Heisenberg chain, we also see almost ballistically moving trajectories that carry torsion in a thermal state. And again, if you didn't know about the torsion, you wouldn't have seen it, because if you look at something like the magnetization, the Z component, That in both cases looks diffusive or super diffusive because magnetization gets screened during collisions in a thermal state. So if you didn't know about the torsion, you wouldn't have found these ballistically moving things in the Heisenberg chain that are very highly localized and carry this torsion ballistically, essentially. And now the question is, can we make that a bit more quantitative? These are kind of nice pictures. So can you ask the question, we know the Ishimori chain is a gas of solitons. Is the Heisenberg chain also a gas of soliton in some sense? So the idea would be to expand a thermal state into a vacuum state and ask, do I get solitons out? And this is exactly what is called kind of the scattering map or the inverse scattering map, where initially I have a system of size L that is presumably a soliton gas. If I then embed it into a large infinite system, wait for a long time, these solitons that were dense will become dilute, they will become fully separated, and then I can define good quantum numbers for them, which then, if I propagate them backwards, define what my original kind of distribution of the soliton gas was. And that's what we're going to do both for the soliton and Ishimori chain. So left will again be Ishimori, right will be the Heisenberg chain. I'm going to take a thermal state of 100 sites, embed it in a vacuum state, and I'm now going to expand this state into vacuum. But if I wait long enough, the Ishimori chain, this thermal mess of lots of fluctuations, nicely separates into individual peaks, which are the solitons that we know the Ishimori chain is composed of. But if I showed you this picture for the Heisenberg chain, you couldn't really tell a difference. So the Heisenberg chain in practice seems to have a very high overlap with well-defined solitons in the sense of an inverse scattering map that can really kind of separate them out and get well-defined solitons out of thermal states of the Heisenberg chain. So this seems to suggest that at least in some limit, the Heisenberg chain can be described as a gas of solitons, which then brings me to my last point. So we've seen that thermal states seem to contain long-lived solitons. These solitons seem to scatter almost integrable, as in the Ishimori case. And then, of course, we know that magnetization transport is screened by collisions, which I demonstrate here. So if the narrow soliton hits the wide soliton, it had a well-defined magnetization before. During collision, it kind of flips the spin, as in the quantum XXZ chain. So that is why spin transport is not diffusive. However, this now tells the same story that we know about KPZ scaling the XXZ quantum Heisenberg chain. So we know we have solitons. We know the magnetization transport is screened, but we can kind of could hope that the same mechanism that gets KPZ in the quantum case now seems to be active also in the classical Heisenberg chain, which then could be a potential explanation why we saw this extended KPZ scaling regime for the ferromagnet. And with that, I kind of want to conclude the second part. So what I've shown you is that the classical Heisenberg chain, thought to be non-integrable, thought to be one of the most simple dynamical models of magnetism, actually has a super diffusive regime in the ferromagnet, at least for some very long time scale, where it also shows perfect collapse onto a KPZ scaling function for the ferromagnet. And the explanation I wanted to put forward here is that this could be explained by kind of a connection to an integrable Ishimori chain, where really the solitons in the Heisenberg chain descend from solitons of a close by, where close by isn't really well defined integrable model, with the surprising finding that we have exact solutions for stationary solitons and at least adiabatic solitons for moving solitons for the Heisenberg chain, which previously, to our knowledge, haven't been known to exist in the simple ferromagnet Heisenberg model. In addition, these solitons turn out to be not only one-soliton solutions, but also scatter almost integrably in the sense that, you know, they're scattering phase shifts and they live forever, even for hundreds of collisions, and that thermal states essentially are composed of these kind of soliton-like objects, which then could explain why we saw this KPZ regime. And with that, of course, I want to thank Rildrich, Masoud, and Adam, who did a lot of the work. The first part is published. The second part will be on arXiv soon. I should acknowledge funding sources. If you have any questions on this project or anything else that I worked on, you know, contact me. Here's my email. I will move to Oklahoma and will have PhD and postdoc positions. So if you're interested in anything I've talked about or other stuff, you know, contact me. Yeah, and I'm open for any questions.
Okay, thank you very much for your talk. And we are running a bit behind the schedule, but I think we can still take a question or two. Okay. Yeah. Question from our director Sergey.
Yeah, Thomas, I guess I have lots of questions, and that's not the right time right now to discuss them all. But let me just ask one.
Yeah.
So this is coming back to this issue of the other conserved quantities.
Mm-hmm.
So just one cross, so to say, reference to a non-integrable, one of the many non-integrable discrete nonlinear Schrödinger equations, which conserve energy and some total norm, some classical analog of the number of particles, let's say. So in that case, what people worked out quite some time ago, or tried to work out, is how the microcanonical dynamics can be mapped onto a canonical one, meaning that if you evolve a microcanonical system at the two given densities, let's say of energy and something else, call this norm density, how would that map onto a pair of temperature and chemical potential, for instance? And then the surprise was that this works only in a part of the microcanonical phase space diagram, which then was labeled Gibbs part. And as you can guess, there is therefore another part which is non-Gibbs, where the construction of a Gibbs function fails.
Right.
And up to now, not much is known about what the microcanonical dynamics is doing there exactly, and what kind of distribution functions one has to use in order to describe it on a statistical mechanics level. Did you try anything like that here as well? Or do you?
Yeah, we thought about it exactly for those reasons, because I was never sure about what canonical, microcanonical, what we're actually doing. So it's a bit hard, because it's hard to extract construct an exact state that has a given energy density at exactly zero magnetization and still call it thermal. But what we tried is, imagine you sample a thermal state, and then you just change one spin a bit to make the magnetization zero. If the magnetization is kind of already thermodynamically small in 1 over L, then that is an energy change that is essentially negligible in a thermal ensemble, because you have energy fluctuations in it anyway at a finite temperature. So that doesn't really change your thermal ensemble too much. It does, of course, move you in a slightly different energy ensemble. But we tried that, and the m equals 0 simulations were consistent with the ones where we didn't try to constrain to m exactly equal to 0. So at least in some regime, they look comparable, but I couldn't claim that for all choices of energy density and magnetization density, the results would be the same.
Okay, thank you. I'll try to reach out to you later.
Yeah. I'm happy to talk about any of those things.
Okay, any other question? Yeah, actually, I think it's lunchtime in Korea.
Yeah,
oh,
okay.
Yeah,
okay,
okay.
Great.
So what
thank you for the invitation. Enjoy your lunch.
Oh, there's one question.
Just one quick question. Thanks for the very nice talk. So I am wondering what happens to this antiferromagnetic case. So you argued that we can use this adiabatic connection from Ishimori chain to ferromagnetic chain. But if I guess if gamma becomes negative, I guess this Ishimori chain becomes negative.
So I think gamma negative might not make sense. So the problem of the antiferromagnet is the vacuum isn't well defined. The vacuum with an antiferromagnet, and that causes trouble, because the Ishimori chain in the antiferromagnet has an infinite density, right? It's a log of 1 plus s dot s. If s dot s is -1, that's log of 0. So it has infinite energy density for the antiferromagnetic background. So that's why it doesn't work for. That's one reason why it doesn't work for the antiferromagnet. So you can't connect it directly to the Ishimori chain.
I see. Okay. Okay. It makes sense. Okay. Yeah. Yeah. It makes sense. Thank you.
Okay, so I think we should close our session here, and thanks again to our two speakers for their wonderful talks.